Welcome to this lecture about the standard deviation and the variance. In the previous lectures, we discussed different measures of the central tendency, and measures such as the range and the interquartile range that are used to describe the spread of the data. In this lecture, we'll discuss the standard deviation and the variance, which are two other measures that are used to describe the spread of the data. At the end of this lecture, we will compare the interquartile range and the standard deviation and discuss which measure that is most appropriate to use. Remember from the previous lecture about the sample and the population that SD or S denote the sample standard deviation, whereas sigma denotes the population standard deviation. The sample variance is denoted as the square of S, whereas the population variance is denoted as the square of sigma. The standard deviation of a sample is calculated by the following formula, where x sub I is the values of our observations. X bar is the mean of those observations, and n is our sample size. In other words, n represents the number of data points we have. The reason why we divide by n minus 1 and not just by n is because we will get an unbiased estimate of the sample variance. This will be discussed further in a separate lecture. This part of the formula shows that we should sum the square differences between the observations and the mean of those observations, and divide by the sample size minus 1. Suppose we have measured the height of 3 plants. The height of those 3 plants was 2, 4 and 6 decimeters. To calculate the sample standard deviation of variable x, we start to calculate the mean. The mean height of the 3 plants is equal to 4. We can illustrate the mean height of the plants in the plot like this. Next, we calculate the square difference between the data points and the mean. We therefore take our 3 data points minus the mean that we previously calculated to 4. For example, the difference between the height of the first plant and the mean is 2, and the square of 2 is 4. The difference between the first value and the mean can be seen as the distance between the shortest plant and the mean. The second data point has the same value as the mean, which means that the data point and the mean have the same location. The distance between this data point and the mean is therefore 0, and the distance between the tallest plant and the mean is shown by this arrow. Next, we sum the square differences. We see that the sum of these values is 8. Finally, we'll plug in our values in the equation for the sample standard deviation. We know that the sum of the square distances between the data points and the mean is 8, and that n is equal to 3 since we have 3 data points. We see that the standard deviation is equal to 2 in this example. The standard deviation is usually presented in association with the mean like this, where the first value represents the mean and the second value the standard deviation. This notation actually represents an interval between 2 and 6 because 4 minus 2 is 2 and 4 plus 2 is 6. If we move one standard deviation away from the mean, we get an interval that goes between 2 and 6. The standard deviation is usually represented graphically in bar charts, where the height of the bar corresponds to the mean, and the so-called error bar corresponds to one standard deviation. Sometimes the error bar is also drawn below the mean like this. The range of this error bar corresponds to the range we calculated earlier. However, how do we interpret this range? If we see something like this, we know that about 68% of the data points can be found in a range between 2 and 6. If the error bars in a bar chart represents one standard deviation, We know that about 68% of the data points can be found within these error bars. Since we only have 3 data points in this example, it is difficult to imagine this. However, suppose we instead had measured the height of 70 plants and plotted them like this. The corresponding bar chart would then look something like this. We can now interpret this error bar as the range where we will find approximately 68% of the data points, given that the data is normally distributed. We'll now have a look at the so-called sample variance. The sample variance is related to the standard deviation. The variance is denoted as the square of S, simply because it is the square of the standard deviation. The variance is also computed by adding the square differences between observations and the mean, and then divide by n-1. However, we do not take the square root of the expression as we do for the standard deviation. Therefore, if we know the standard deviation, we can square it to get the variance. In our previous example, we found that the standard deviation was equal to 2. Therefore, the square of this value gives us the variance. If we ignore -1 in the denominator, the variance can be seen as the mean of the square differences between the data points and the mean value. Similarly, the standard deviation can be seen as the square root of the average square differences between the data points and the mean. In comparison to the standard deviation, the estimated value of the variance has no simple interpretation and is therefore usually not used as a measure of the spread. The variance is mainly used in theoretical statistics. Okay, so we now know how to calculate the interquartile range and the standard deviation. However, which measures should we select to describe the spread of the data? The choice between the standard deviation and the interquartile range follows the same arguments as for the mean and the median. Generally, use the standard deviation in association with the mean, and the interquartile range in association with the median. Remember that one standard deviation away from the mean covers about 68% of the data, given that the data has a normal distribution, and that the interval between quartile 1 and quartile 3 covers the middle 50% of the data points. This was the end of this lecture about different measures for the spread of the data. In the next lecture, we will have a look at the normal distribution.